Hi there, my name is Emily.
My name is Tim.
I'm Zhiheng.
And we did our project on computational modeling of aortic valve calcification, investigating various methods of modeling, functional analysis via normal force, and its future applications for treating cardiovascular disease. To provide a bit of background, aortic valve calcification occurs when calcium deposits thicken and stiffen the valve cusps, affecting their ability to properly open and close over time. Over a course of decades, this leads to aortic valve stenosis, which results in reduced blood flow through the valves. This is important because in the US, it is estimated that 26,000 people die from aortic valve disorders annually, and by 2020, it is predicted that 800,000 people worldwide will need heart valve replacements each year, aortic valves. Additionally, the paper models functionality of calcified valves over decades rather than one point in time, and accomplishes this by comparing valve thickness and stiffness as a function of age, with increased age yielding increased calcification area on the valves. Finally, the paper assumes a simple growth law, accounting for both calcification initiation and growth over time.
From other people's study, we found that each triplet of the valve forms a semi-spherical shape together with the aortic blood vessel wall. Based on this finding, we just built our basic model, which is besides other people's model. For each triplet and blood vessel complex, we build up the model shown in the middle. The dark brown part is the valve, while the orange part is the blood vessel. However, this model is still hard to analyze because it contains two materials with different Young's modulus. To simplify the calculation, we treat the complex made from single material having an equivalent Young's modulus. The graph on the right shows the condition we perform the analysis. The right part is the left ventricle, while the orange part is the complex. R1 is the inner radius of the complex, while R2 is the outer radius of the complex. So here's the scheme we built our computational model based on. P2 is the blood pressure in left ventricle, while P1 is the blood pressure in aorta. The free body diagram and the stress analysis is performed on the right. So here's a calculation in the computational model. The 5 equations in 2 brackets are from Zhiheng and equilibrium assumption. By solving all these equations, we finally find the relationship between the change in radius and the change in pressure. By using the geometry from the good old days, we finally find the size of the opening area of the valve.
Under the assumption of no pressure inside and outside of the sphere, we found the inner radius to be 13 mm and the outer radius to be 14.5 mm. At a pressure of 90 mmHg, the inner radius was 13.18 and the outer radius was 14.68. When we assume the outside pressure to be 150 and the inside pressure to be 90, the inner radius was 8.857 and the outer radius was 10.357. And we calculated the opening area of the valve to be approximately 710 mm squared, which is half of the original cross-sectional area. Our model provided a slight underestimation of the opening area, and this may be caused by the rough estimation we made for the Young's modulus. One limitation for our model is that the junction between valve and blood vessel was not considered. Another limitation is that the Young's modulus used in the study was a very rough estimation of the system. Finally, our model didn't consider the effect of gravity and various shear forces. So in a future study, we should use a better estimation of the Young's modulus and also take into account the effect of gravity and shear components on the system. We would like to thank our wonderful professor at GSI for their help.